Welcome to the third session of BSc Physics. The topic of discussion is atomic physics. I am Dr. K.N. Jagadish. The contents of this session are the Sommerfeld's atom model and its application to explain the electron orbits. In the previous session, we have learned about the failures of Bohr's theory. One of the important failures of Bohr's theory is its inability to explain the fine structure of hydrogen atom. According to Bohr's theory, whenever there is a transition of electron from higher orbit to lower orbit, a single photon of definite energy is produced, leading to a well-defined spectral line. But observations reveal that the spectral lines of Balmer series like H alpha, H beta, H gamma, H delta, etc. are not single lines as predicted by Bohr's theory. When the spectral lines were observed through high-resolution spectrometers, each line is found to contain many component lines. Accordingly, H-alpha line is not a single line, but made up of three closely spaced lines of slightly different energies. Similarly, other lines of different series are also not single lines, but made up of group of lines. This is called the fine structure of spectral lines. To explain the fine structure of spectral lines, Sommerfeld made two important modifications to the Bohr model. The first modification is the electrons move around the nucleus in elliptical orbits instead of Bohr's circular orbits. Hence, the velocity of the electron moving in an elliptical orbit varies considerably at different parts of the orbit. The second modification is this variation in velocity introduces relativistic variation in the mass of the moving electron. The mass of the electron varies with velocity according to the relation m equals m0 divided by root of 1 minus v square by c square, where m0 is the rest mass of the electron, v is the actual velocity of the electron in that orbit, and c is the speed of light. Now, to understand the actual application of these modifications, let us consider an electron moving in an elliptical orbit around the nucleus. Now, the position vector can be fixed in terms of the polar coordinates r and theta, where r is the radial component and theta is the angular component. Now, In the figure, the radius vector r varies as the electron moves along the elliptical path, and so also the angular component theta, which is called as the azimuthal angle, also varies as the electron moves along the elliptical path. In case of circular orbit, only one coordinate theta varies periodically with respect to the x-axis. But in case of elliptical orbit, not only does the angle vary, but the length of the radius vector r also varies periodically. The tangential velocity v of the electron at any instant can be resolved into two components, one along the radius vector called the radial component Pr, which is given by dr by dt, and the other at right angle to the radius vector called the transverse component v theta, which is given by r into d theta by dt. Now we have to quantize the momentum associated with both coordinates r and theta in accordance with Bohr's quantum condition as follows. The surface integral of the radial momentum Pr dr must be equal to nr into h, and the surface integral of p theta into d theta must be equal to n theta into h, where Pr is the radial component of momentum, which is given by m into dr by dt, and the transverse component p theta, that is the angular momentum. The angular momentum is equal to m into r into d theta by dt, using the idea of motion of a particle in two dimensions. Here, n theta is the angular or azimuthal quantum number, and nr is the radial quantum number. N theta and nr, the two quantum numbers, can take only positive integral values such that their sum n theta plus nr is equal to the principal quantum number n. And this principal quantum number n can take only integral values, that is 1, 2, 3, etc. To determine allowed elliptical orbits, we have to evaluate the two integers n theta and nr. First, by making use of the first integral of p theta d theta is equal to n theta into h. After integration and substituting the limits, we get p theta as equal to n theta into h divided by 2 pi. On the same lines, we can also show that nr into h is equal to n theta into h divided by 1 minus epsilon square whole to the power of half minus n theta into h, where epsilon is the eccentricity of the ellipse. Now, substituting the values, we can get the sum of the two quantum numbers, nr plus n theta, is equal to n theta divided by 1 minus epsilon square to the power of half. We know that nr plus n theta is equal to n. Therefore, substituting on the left-hand side, we get n as equal to n theta divided by 1 minus epsilon square whole to the power of half. From this, we can arrive at the expression 1 minus epsilon square as equal to n theta square divided by n square. We are familiar with the standard equation for an ellipse as 1 minus epsilon square is equal to b squared divided by a square, where a is called the semi-major axis of the ellipse and b is referred to as the semi-minor axis of the ellipse. Now, comparing the two equations, we can show that b squared divided by a square is equal to n theta square divided by n square, or b by a is equal to n theta divided by n. Now, this equation is the condition for allowed elliptical orbits. The allowed elliptical orbits are those for which the ratio of major and minor axes is that of two integers. Now, let us substitute as a first condition when n theta is equal to n. It implies b must be equal to a, which means the orbit is a circular. Condition 2, when n theta is equal to 0, then b becomes equal to 0. This shows that the ellipse degenerates into a straight line passing through the nucleus. Hence, n theta cannot take 0 value. The third condition is when n theta is greater than n, then b must be greater than a, which is not possible for an ellipse since b is always less than a. Hence, n theta can't be greater than n. Now, coming to the application of Sommerfeld model for the different orbits. For the first orbit, the principal quantum number n is equal to 1. We know the condition that nr plus n theta is equal to n, which means nr plus n theta is equal to 1. And n theta is not equal to 0. That means n theta must definitely take the value equal to 1. As n is equal to 1 and n theta is equal to 1, the first orbit is a circle. Coming to the second application, for n equals 2, n theta can have two values, that is 1 or 2. For n r plus n theta equals 2, n theta can be 1 and n can be 2. Now, this gives rise to the elliptical orbit, since the value of n theta and n are different. If n theta is equal to 2 and n is equal to 2, the resulting orbit is a circle. The orbits are represented as 2, 1, 2, 2. For n equals 3, n theta can take three different values of 1 or 2 or 3. If n theta is equal to 1 and n equals 3, the orbit is definitely an ellipse. If n theta is equal to 2 and n equals 3, once again, the orbit is an ellipse. If n theta is equal to 3 and n equals 3, since the two values are same, definitely the orbit is a circle. The different orbits here are represented as 3, 1, 3, 2, 3, 3. In the above representation, the subscript is the azimuthal quantum number n theta. Thank you.